Thank you so much for that warm introduction, and hello to everybody all across the world. I think we have a pretty global audience today, and I'm very, very happy to speak to you. So as Safal said, my name is Michael Reid. I'm a professor of astronomy at the University of Toronto in Canada, and my specialty is astronomy. And today I'm going to talk to you about a really, really fascinating topic in astronomy these days, which is the search for another planet like our own Earth. And we're going to have lots of opportunity for you to ask questions. I believe you can type them in the chat on Zoom, and Safal will relay them to me. So definitely, if you have questions as we go along, feel free to put them in the chat, and I'll try and answer as many of them as I can. Delighted to answer questions. So to start us off, I want to start close to home, right? And so let's start actually at home. This is our own planet Earth. And the overwhelming majority of our lives, we spend, almost all of us will spend it on this planet, and we spend almost all our time thinking about things on this planet. It's a beautiful planet. This is an early picture of the Earth taken by astronauts on their way to the moon, and it's famous because it's one of the very first photos ever taken that showed Earth from outside, from a perspective that we don't normally get in our daily lives, right? We normally spend all of our time kind of, dealing with our very close personal environment, and we don't think about the much bigger picture of things. So this picture kind of touched off a bit of a revolution in that it got people to start to think about our planet as a whole, as one single object that we are all connected via. And you can see also in this photo that it's floating in this very inky blackness, right? It's a kind of vulnerable sort of place. It's got all these beautiful oceans and forests and things on the surface, but surrounding it, there is this inhospitable void where it would be very difficult, maybe impossible for life to survive. There's no air out there. It's extremely cold, all sorts of dangers. So it started us thinking about how special life really was. It exists all over the Earth, but does it exist anywhere else? So as an astronomer, my job is to look in the other direction, not down towards Earth, but out towards the cosmos. And this is an equally revolutionary picture of the universe. And this is a very, very special picture that it sort of bears thinking about how this picture was taken. So this is a picture taken by the Hubble Space Telescope, which is one of the most powerful telescopes we've ever built. It's a space telescope, meaning it orbits around the Earth. And because it's up in space where it doesn't have to look through the atmosphere, the air on Earth, that allows it to see very, very clearly to extremely far distances. And the way this particular photo was taken was by pointing the Hubble Space Telescope at a tiny, tiny, tiny patch of sky. So to get a sense of how small this patch of sky is, if you hold your pinky fingernail out at arm's length, right, that pinky fingernail is about as big on the sky as the patch you are looking at in this picture. So it's just a tiny, tiny speck of the sky. And the Hubble Space Telescope was pointed in this direction, and they left the shutter on the camera, if you like, open for days and days to gather lots and lots of light from the most distant things that we can see. And this is the resulting picture. It's called the Hubble Deep Field. It's an image of some of the farthest things we can see. But what's special about this image is that except for a couple of points of light, so maybe you can see if I hover over them with my mouse. Let me just bring up my pointer here. So except for a few points of light like this one in the lower right and this one in the upper left, almost every point of light in this image is not a star. These points of light are galaxies. Each of these galaxies is like our own Milky Way galaxy. Maybe you know that the Earth and our solar system are part of a larger object called the Milky Way galaxy. Our Milky Way galaxy contains about 500 billion stars. That's 500,000 million stars. It's a lot of stars. You could spend your whole life just counting the stars in our own Milky Way. It would take you your whole life. But in this picture, you're seeing hundreds of thousands of galaxies beyond our own Milky Way. So each of these lights, this one and this one and this one, all the little tiny faint ones in the background, those are galaxies. Each one of them is hundreds of billions of stars. So it would take, the lifetime of everyone on Earth put together to count all of the stars in all of these galaxies. And this is just a tiny, remember, it's like your fingernail, tiny little speck on the sky contains this many galaxies. And so as an astronomer, when I see a picture like this, it's really, really hard for me to believe that with all those uncountably many stars, that none of them would have a planet like Earth. That's possible, but it's a bit hard to believe that of all those stars in our massive universe, we would be completely alone. And yet, we have yet to actually find another planet that is like Earth or life on any other planet in the universe. And so that's something that needs a little bit of explaining. Why haven't we found another planet that is just like Earth? Well, first of all, let's talk about what do we mean when we say a planet that is like Earth? What makes a planet Earth-like? So there are a lot of things that go into making a planet. But if I jump back to this picture of our planet, if you've looked at pictures of other planets, you may immediately recognize what makes this planet different from most of the other ones that you will have seen. And that is, in particular, the blue stuff all over the surface of the Earth. This is, of course, liquid water, our oceans and lakes and rivers, which Earth has in huge abundance, but most other planets have. So, whoops, I seem to be losing my picture here. So most other planets don't have this water all over the planet the way we do. So when we think about trying to find a planet that is like Earth, one of our most important criteria is looking for liquid water. The thing that makes Earth special to us is that it can support life. We can live on Earth much more easily than we could live on any other planet. And the thing that makes it possible for us to live on Earth is all this liquid water everywhere. So when we think about finding a planet that is like Earth, one of our major criteria, one of the things we look for is water. And we have this sort of motto, follow the water. So there are lots of other things that make Earth a nice planet: the temperature, the amount of light, the chemical composition of the atmosphere, things like that. But the sort of key thing that seems to make Earth what it is the liquid water. So that's the main thing that astronomers look for. We look for planets that have liquid water on the surface. Now let's talk about, why does Earth have liquid water on the surface? Well, here is a drawing of some solar system. And you can see there's a star on one side of the diagram here. And that star provides heat and light to the planets that orbit it. But you have to be at just the right distance from the star in order to get just the right amount of heat and light to keep your planet warm, but not too warm. So if you have a planet that's too close to the star, like the one labeled too hot here, then that planet is a little too close to the very hot star. It's going to be too hot. Any water on the surface of that planet will evaporate and boil away from the planet. But if you're too far from the star, then you don't receive enough sunlight and enough warmth from the star. And then your planet will be too cold and all of the water will freeze solid. And of course, it's still nice that the water is there. It hasn't boiled away, but it's frozen. And most life that we know of doesn't do very well frozen into a solid block of ice. So you have to be just right. You have to be in between the too close and too far distances for your planet to sustain water, to have oceans on it for long periods of time, long enough for life to develop and become complex and maybe even become intelligent, like life on Earth. So this is the big thing. We look for planets that are in this sort of green region here that we call the habitable zone. Habitable means a planet that could have life on it, because it's really life that we're looking for when we look for a planet like Earth. So if a planet is at the right distance from its parent star in this range of distances where it can be the right temperature for liquid water, we call that the habitable zone, and we look for planets in the habitable zone around other stars. So in our own solar system, we can ask the question, well, which planets are in the habitable zone? As you may know, there are 8 planets in our solar system, and in order from the sun, that's Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, and Neptune. And of those planets, only 2 are maybe in the habitable zone. So clearly Earth is in the habitable zone of the sun. There's a lot of water on the surface of the Earth. That's great. It's at the right temperature for water. The other planet that may or may not be kind of just on the edge of the habitable zone is Mars, which we'll come back to in a little bit. But the other planets, Mercury, Venus, too hot. Jupiter, Saturn, Uranus, and Neptune, they're not only too cold, they're the wrong kind of planet. So those planets don't have a solid surface. So even if there was water in them somewhere, those planets are kind of big balls of gas and liquid. They're not the same kind of planet as the small inner planets are. So we wouldn't normally look for, they're not similar to Earth no matter where they are, basically. So we can look at the planets in our own solar system and try and learn, why are some of them habitable? Why are some of them able to support life while others are not? So a really interesting planet to look at is Venus. This is the planet Venus. It's the next closest planet to the sun after Earth. And in a lot of ways, Venus is almost an identical twin to Earth. It's the same size, it's the same mass, meaning it has the same amount of gravity. It has basically the same chemical composition. It's made of the same things. And yet it is completely different from Earth in terms of its ability to support life. So why is that? Well, you may get a clue by looking at this photo. So this photo of Venus doesn't look at all like a photo of Earth, right? There is a rocky surface to Venus, just like there is to Earth, but you don't see any oceans in this picture. In fact, all you see are clouds, because the entire surface of Venus is shrouded in thick clouds all the time. There's never any breaks in the clouds, basically. So if we compare Venus with Earth, here's our old friend Earth, and a few facts about it. So the average temperature on Earth, if you sort of take the temperatures over the whole planet, in general, it's about 15 degrees Celsius overall on Earth. The atmospheric pressure, so that's the sort of amount of atmosphere we have, the amount of gases that surround our planet, we define that as 1 atmosphere, okay? That's just whatever Earth has, we're gonna call that 1. And then our atmosphere has, as you may know, a particular gas in it called carbon dioxide, CO2. And that gas is only present in tiny, tiny, tiny quantities in our atmosphere. But it is hugely important to life on Earth because, as you are probably aware, this gas is what we call a greenhouse gas. It's a kind of gas that can trap and hold sunlight and keep a planet warm. Or, as we're currently worried about, it can make your planet too warm if you have too much of it. So on Earth, we just have a tiny, tiny, tiny amount of carbon dioxide. But if we contrast with Venus, look at how different it is. On Earth, it's about 15 degrees Celsius. On Venus, 460 degrees Celsius. That's as hot as your oven, your kitchen oven, on its maximum temperature. It's hot enough to melt some metals. So when we have sent spacecraft to the surface of Venus, they survive for maybe minutes to hours before they're destroyed by the immense heat. The atmosphere on Venus is 92 times thicker than the atmosphere on Earth. It's so dense, the atmosphere on Venus, that if you could stand on the surface, you would feel it crushing you. It's so thick. And 96% of it, almost the entire atmosphere of Venus, is carbon dioxide. So whereas on Earth, we have 0.04%, just a tiny amount of carbon dioxide, and we're so worried about it going even a little bit higher. On Venus, 96% carbon dioxide. And that is why the temperature on the surface of Venus is 460 degrees, because that carbon dioxide is grabbing and holding all the heat from the sun. and it's just turning the planet into an oven. It's a terrible, terrible kind of place. This is what we're worried would happen to Earth if we just keep putting carbon dioxide into our atmosphere. It would become more and more and more like Venus. We don't want that to happen. So on the surface of Venus, this is what it looks like as a result. This is from a Russian spacecraft that landed on Venus many years ago and took some pictures. And you can see it's not a very nice place. I don't know about you, but I wouldn't want to live there. There's nothing alive. It's boiling hot all the time. It's cloudy all the time. It rains acid on Venus. It's a terrible, terrible place, not some place you'd want to go. So this is why, even though Venus is sort of like Earth, you know, from a distance, you'd say, yeah, it's about the same size, about the same mass, that kind of thing. But it's really actually unlike Earth because of its atmosphere. So this is the planet Mars. And actually, this is my favorite ever picture of Mars. And oh, I think somebody's found the annotate function in Zoom. Maybe please don't do that for now. Thanks. Okay, so this is the planet Mars. And as I say, this is my favorite picture of Mars. It's a relatively recent picture of Mars. And I don't know if any of you, maybe you're recognizing this and you're kind of cheering a little bit because you know this photo. It's an absolutely gorgeous picture of Mars, and it was taken by the Indian Space Research Organization. So you may know that India, a couple of years, or about 7 years ago now, launched a spacecraft to Mars. And it has orbited Mars and taken amazing photos of Mars. And this is one of them. It's a beautiful, beautiful photo that captures the planet really, really well. So we often call Mars the red planet for maybe obvious reasons when you see this photo. So again, does it look like Earth? Not really. But even though it doesn't at first glance look like Earth, you don't have oceans and things like that, it actually is pretty similar to Earth in a lot of ways. So let me kind of contrast the two of them for you again, the same way we did for Venus. So on Mars, Mars is a smaller planet than Earth. It's, you know, sort of like a quarter the size of Earth. And it is a fair bit colder. It's minus 60 degrees Celsius on average on Mars, which is pretty cold, but not so cold that you couldn't survive, right? Minus 60, that's about the same temperature it gets to in maybe Antarctica on Earth. So it's really cold. You wouldn't probably want to live there, but you could live there with the right equipment. However, on Mars, there's almost no atmosphere. The atmosphere is just a tiny, 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 tiny thin fraction of Earth's atmosphere, which means there's nothing to breathe. So you would need to have oxygen or you know, breathable gases brought with you to Mars, water vapor and things like that to help survive on Mars. But you could. The atmosphere that Mars does have is mostly carbon dioxide, just like Venus. But because the atmosphere is so thin, it still doesn't hold much heat. So Mars being farther from the sun, having a very thin atmosphere that doesn't trap much heat means it's very cold, but not so cold that you could never survive there. So if we look at the surface of Mars, this is what the actual surface of the planet Mars looks like. It looks a little bit like probably some places some of you may have been, you know, like a lot of deserts on Earth. If I didn't tell you this was Mars, you might think this was, you know, the American state of Arizona or Saudi Arabia or the Gobi Desert in China, right? It looks like a lot of places on Earth. The one thing you don't see, though, is plants or animals or any kind of life, because as far as we can tell, there's no life on the surface of Venus, or at least nothing, you know, big, nothing you can see with your unaided eye, no trees, no, you know, animals walking around and things like that. But there might be, you know, kind of bacteria or tiny, tiny microscopic organisms. So why do we think that? Well, here's a different photo of Mars taken from orbit. And I want to draw your attention to the white thing at the bottom of the planet there. That's an ice cap. So Mars, just like Earth, has ice caps, just the same way that the North Pole and the South Pole of the Earth have ice in great big sheets at their poles. Mars has the same thing. It has ice at its poles. And some of that ice is water. It's frozen, you know, which again, we can't really live in the frozen water, but at least it's there. And the thinking is that a long time ago, a lot of that water would have been liquid. So if this is what Mars looks like today on the right, the red planet, very dry and parched and cold, we believe this on the left is what Mars would have looked like billions of years ago. So a long time ago, Mars had a thicker atmosphere, And it was enough to trap more light from the sun, keep it warmer, and keep water liquid over the surface of Mars. So we believe Mars had a thin ocean for a fair amount of time, maybe long enough to produce life and life or Earth-like conditions on Mars. So that's of course gone now. The oceans have evaporated away into space and they're no longer able to support life. But we kind of hope that maybe there would have been some life that could have survived this transition as the planet got colder and colder and the water went away. Maybe some life could have survived. So those are the planets of our own solar system. Mercury, not habitable. Venus, definitely not habitable. Earth, nice and habitable, right? We can live on Earth, it's not too difficult. Mars, maybe. But if we're looking for another Earth, there's nowhere else to look in our solar system for a planet that's just like Earth. There's nothing left. The other 4 planets are big gas planets. They're not like Earth at all. So where we mainly look these days is not in our own solar system, not at planets orbiting the sun, but at planets orbiting other stars. And so as I showed you before, there are so many stars, millions, billions, trillions of stars in the universe. And now what astronomers are doing is spending a lot of time trying to see planets orbiting those stars to see if they might be like Earth. So the thing is, though, that's really tricky. So why is it tricky? It's tricky for the same reason that if you take your camera and you try and take a photo of a bright light, say a car headlight or a stadium light, something like that, and I tell you that there is a tiny, tiny, tiny firefly, you know, a little insect that has a tiny, tiny little glowing bottom sitting on that bright light. And I ask you, take a photo of that little bug with your camera. It's almost impossible. Your photo will look like this. All you will see is the incredibly bright light from the car headlight or the stadium light or whatever. And you won't be able to see the little firefly. And that's exactly the same sort of situation we run into when we try and take pictures of planets in other solar systems. All we can see is the glow from their stars that they orbit. So if you imagine aliens looking at our own solar system and trying to take a picture of Earth, mainly what they would see is the sun. It's so bright, it just blots out everything else in the photo and you can't see the Earth. So this is really, really challenging. And we have just begun to make progress in maybe taking some photos of planets orbiting other stars by using a whole bunch of technology to try and get rid of the light from the star. And when it succeeds, this method, it looks like this. So this is a little movie of 4 planets orbiting another star, not the sun. This is a different solar system, maybe where somebody else lives. And what you're seeing in this movie, the little yellow little yellow star symbol in the center is where the sun in that solar system would be, but it's been removed from this image. So all that kind of junk you see in the middle of the image is where, using a whole bunch of different techniques, we've tried to get rid of all the starlight so that we can see the planets. And these 4 dots that you see moving around the star in the center there, those are the 4 planets in that solar system. And unfortunately, though, they are not Earth-like, and we can't currently take pictures of Earth-like planets. These are really big planets like Jupiter in our own solar system, even bigger than Jupiter. And they're really far from the star and they're really hot. Or in some cases they could be cold, but these ones happen to be really hot because they're very, very young. But there's no way they're Earth-like. And this is the best we can currently do. We can see really huge planets that are really warm and really young, not at all like Earth. So from the perspective of looking for Earth-like planets, the methods that we use are not taking pictures. The methods that we use are what we call indirect methods, where we don't see these planets orbiting other stars, but we can we can deduce that they are there based on observations of just the star. So let me show you how that works. So this is a little movie showing you a video of a star. So this would be a star in some other solar system, not the sun. And you see there's a little black dot passing in front of that star. Now, we don't have telescopes powerful enough to actually see something like that. we can't take a picture like the one you're seeing in this movie. But what we can do is very carefully monitor the brightness of that star and try and measure how does its brightness change with time. And what you can sometimes see with different stars is that as a planet passes in front of the star, the light from the star will dip just a little bit. And that's what's being shown on the graph at the bottom. So normally the star has a certain brightness, and then just there, when the planet starts to cross the star, it blocks some light from the star. The star appears to dim just a tiny, tiny, tiny bit as long as the planet is in front of it. And then when the planet clears the other side of the star appears to brighten again because the light is no longer being blocked. So we call this the transit method because when a planet passes in front of a star, we call that a planetary transit. So this transit method is actually really good for finding Earth-sized planets. Even if a small planet like the Earth passes in front of the star that it's orbiting, we can detect the tiny, tiny drop in the brightness of the star and work out what kind of planet that would have been. And we have used this method very successfully now to find a whole bunch of different planets orbiting other stars. So on the bottom of this diagram, you see a diagram of our solar system. And again, you see the sun is the thing in the center. So oops, where did my cursor go? Right here, this is the sun in the center of our solar system. And each of the blue lines is an indication of the orbit of one of the planets. So this is the orbit of Mercury, then Venus, and then we run into this green thing that we talked about before. This is a representation of the habitable zone. It's where you could put planets in the solar system and have them be a place where life could survive, where liquid water could survive. So again, you see that the Earth and Mars both orbit inside the habitable zone. But on the top here are two other solar systems. So these are different stars from our own sun. And they have funny names, Kepler 452 and Kepler 186. That's based on the telescope called the Kepler Space Telescope that was used to find them. And then they just give them numbers in order as they find them. So in the Kepler 452 system, it's a star a lot like the sun. And it has a habitable zone, right? The distance you could put a planet where liquid water could last for a long time. And in that habitable zone, there is a planet you see down here in the bottom. This is an artist representation. It's a drawing of what we think that planet might look like. So remember, we can't actually see the planet. What happens is we see that the planet blocks light from the star, and we can work out what kind of planet it is. And we know that this planet is what we call a super Earth. And this is a kind of planet we don't have in our own solar system. We have Earth and Venus, which are, reasonably big, and then Mercury and Mars, which are small. But we don't have any super Earths in our solar system. These are planets that are like Earth. They're rocky, and they have maybe a thin atmosphere, maybe a thick atmosphere, but they're not, a gas planet like Jupiter or Saturn. And we don't know whether planets like Kepler 452b could support life. Maybe they could, but we don't have any of them in our own solar system to be able to kind of test that. So maybe since we've paused a little bit, is there anyone with questions? Is anyone asking questions that we can deal with now? Okay, well, we'll do questions at the end then. So we'll get there soon. Okay, so what we've learned from these other solar systems is that they have planets that are like our own Earth, at least in their kind of overall properties. The Kepler 186 system, you can see, has a planet that is actually very similar in size to the Earth. It's not even a super Earth, it's just Earth-sized. But here's the important thing to remember. Just because a planet is rocky and the same size as Earth doesn't mean it's like Earth. Because remember Venus. Venus is rocky, it's the same size as Earth, basically the same kind of planet. It would block the same amount of light from the sun as Earth does, but it's not really the same. And it's because of that atmosphere. So unfortunately, with this technique, we usually don't know much about the atmospheres of these planets. So we don't know if they're Venus-like or Earth-like, but that's one of the things we're really trying to figure out. So I want to show you one of the most exciting systems anyone has found so far. This is the Trappist1 system, Trappist-1. And it's exciting because it has many planets potentially that could be habitable. So unlike our own solar system, which really has only one, right, Earth, Mars maybe is habitable. But in the Trappist-1 system, there are so far known 7 planets that are approximately similar in size to Earth, and 3 of them orbit well within the habitable zone. Those are the planets we call E, F, and G. So again, we don't know what they look like. This is an artist's representation of what they might look like, but these 3 planets could be Earth-like. And what's even more exciting, this star that they orbit is not very far. So it's what we say about 40 light years away. That means that light from this star takes about 40 years to get to Earth, which is a long time. It's still far. It's much farther than we could send a rocket. We don't have anything like the ability to send a rocket that far away. But it's close enough that as we build bigger and bigger telescopes, we should be able to study these planets in a lot more detail. And maybe, maybe in 20 or 30 years, we might start being able to actually take pictures of these planets like the ones that you're seeing in, an artist's form here, and start seeing their surfaces and seeing, do they have water? Do they have maybe green on their continents, suggesting plants? Do they maybe have lights on the night side of them, suggesting cities and civilizations and things like that? So we'll be able to take pictures like that, not in the next 10 years, but maybe in the next, say, 30 years. So it's a little wait yet, but it'll come. Okay, so that means we have now found, in total, basically thousands of planets of this type. That are, so here's again, just another sampling of some artist rendition of the many types of planets that we have found that are at least broadly similar to Earth. Maybe not identical, but they're around the same size, they're rocky, they're in the right, at the right distance from their star to potentially have liquid water. So again, these are not actual photos, these are artist representations, but they give us a sense of what these planets might look like. And we now know of more than 4,000 planets orbiting other stars, and of those, a few dozen are similar to Earth as far as we can tell. But remember a really, really important thing. Remember when we talked about Venus, the atmosphere makes a huge difference. Just because a planet is the same size as Earth doesn't mean it will be Earth-like. It could have a very thick atmosphere that will trap too much heat. It could have no atmosphere and be cold and nothing to breathe, right? So we really need to know what the atmospheres of these planets are like. And this is the thing that astronomers are working really hard on right now. We want to know, for those planets we find in other solar systems that look tantalizingly like they might be like Earth, we want to know, are they actually like Earth or not? So I'll give you a sense of how we figure this out. Basically what we do, this is a little tricky, so don't worry if this kind of seems too complicated, but I'll give you an explanation, and then if you have questions, you can ask them. So basically, what we do is we do that same method that I mentioned before. We wait for the planet to pass in front of its star, but we look at how the light from that planet varies in different colors. So we might look at how much red light does the planet block from the star, how much green light, how much yellow light, how much blue light, things like that. And depending on what chemicals are in the atmosphere of that planet, so say, for example, if the planet has oxygen in its atmosphere, or water, or carbon dioxide, we can see that it will block different amounts of light of different colors, depending on what chemicals are in its atmosphere. And so we try and work out how much light is being blocked in different colors, and that allows us to get a kind of snapshot of the chemicals in the atmospheres of these planets. So this is a little complicated, but basically what this picture is showing you is for some of the very first planets we've been able to use this method for, we can start to get a sense of which chemicals are in their atmospheres. So this is a measure of the atmosphere of a planet called WASP-19b, right? We give these planets kind of funny names. And it has an atmosphere that we the atmosphere is no good for life, definitely no good for life. It's full of gases that are terrible for human beings. One of them is methane. One of them is hydrogen cyanide, which would kill you. It's very bad. Not a good place for life at all, or at least not life as we understand it. But at least it is, we're proving that we can start to measure what the atmosphere is like. And hopefully we will use this technique to find planets that are more like Earth. Even if the ones that we're doing it with now are not. Okay, so this whole time we've been talking about looking for another Earth. But why are we interested in that? We're interested in it because we want to find life. We want to know, are we alone in the universe? Are there other planets with oceans and forests and people or things like people on them? That's what's really interesting to us, is there life? For a long time, we've thought, well, if there is life in the universe, it will live on planets because we live on a planet and we're the only life we know of. But as we've explored our own solar system more, we've started to realize that maybe we're thinking about this the wrong way. Maybe planets aren't the places we should be looking for life. You might think, well, why? We know life exists on Earth. Why wouldn't we look for places like Earth? Well, here is the reason. This beautiful, beautiful object looks like a planet, but it's not. This is a moon of the planet Jupiter in our own solar system. It's a moon called Europa. And hopefully you can appreciate how beautiful it is. I think it's very, very beautiful. This is a picture taken from a spacecraft that went to Jupiter many years ago. And it took this photo of this moon called Europa. And what you're seeing in this photo, notice that it looks so different from Venus, from Mars, from any of the other planets. And that's because it is a completely different kind of object. What you see on the surface of this planet is ice. The whole surface of Europa is ice, water ice. And all these kind of red lines that you see all over it are cracks in the ice. And that is wonderful because those cracks are there because what's under this ice is liquid water. So just like in the cold parts of Earth where you have ice sheets, you know, in the Arctic and the Antarctic, you have ice sheets that sit on top of the ocean, but they move and they crack and they, you know, bump each other around because the water underneath them is moving. That's exactly what's happening on Europa, this moon of Jupiter. There's ice on the surface, but underneath that ice, there is water and a lot of water. Underneath these kinds of moons, they have, or in the interior of them, they have these thick ice layers that are maybe a few kilometers thick, maybe even tens of kilometers thick. But underneath, there is this ocean of liquid water. And Europa is not even the only one. So Europa is a moon of Jupiter. But as you can see in this photo, we have Saturn in the background. And that's because both Jupiter and Saturn have moons like this, moons that are icy on the outside, but wet on the inside. And this is really important. These aren't places that are a lot like Earth. There's no rocky surface. There's no, you know, mountains and things like that. They're just deep ocean over the entire moon. But that's important because we believe that life on Earth began in deep oceans, particularly in these kind of hot regions at the bottom of the ocean called hydrothermal vents, where heat from the inside of the Earth escaped up into the ocean and warmed it up and allowed life to develop there. And we believe that these moons, there's a whole bunch of them, one called Europa, one called Callisto, Ganymede, Enceladus, and Titan, at least 5 moons, maybe even 6. There's one around the planet Neptune that we believe have oceans. And not only do they have oceans, their oceans contain more liquid water than the oceans of Earth. So that's a lot of water in which maybe life could form and survive for long periods of time. So now when we look for places that might be Earth-like, we look not just for planets, but for moons. So again, here is the planet Saturn in the background. This very thin line across the middle of the diagram is the rings of Saturn, and you can see their dramatic shadows cast on the planet. But this object in the foreground, this circle here, that is the planet, or rather the moon, called Titan. And Titan is, it looks small in this photo, but that's only because Saturn is gigantic. Titan is actually bigger than the planet Mercury. So if we put Titan in orbit around the sun, we would call it a planet. It's really big. And Titan is maybe unique in the solar system in that, like Earth, it has oceans. But unlike Earth, it has a different kind of ocean. So this is a close-up picture of Titan, this moon of Saturn. And you can see in this photo that you can actually see sunlight in this little spot here glinting off the oceans of Titan. So we've actually sent a little robot to go and land on Titan and show us what's under its clouds. And here is some of the view that this robot, the pictures that it took as it went to land on this moon of Saturn. And what you're seeing here is a kind of aerial view as this robot drops into the atmosphere of Titan, showing a lake on the surface of Titan, an actual lake, right? We're looking at Venus, horrible boiling. We look at Mars, well, the ice is all frozen into the ice caps, or the water rather. But on Titan, there's a lake on the surface. Many lakes. Here's the problem. This is a lake. It's not a lake made of water. It's a lake made of chemicals called ethane and methane, which again are not suitable for life like us. But the fact that there's large quantities of liquid hanging around on the surface of Titan suggests to us that maybe it could sustain some kind of life. And like the other moons that I mentioned before, like Europa, underneath the surface of Titan, there are oceans of liquid water. So it's a lot like Earth in one way. Earth has liquid water oceans on the surface, and then underground, we have collections of, what we think of as oil and natural gas. On Titan, it's reversed. The things like oil and natural gas sit on the surface as liquid, and underneath, underground, there is liquid water. So it's a bit like Earth, but sort of reversed, if you will. So a lot of people now are thinking, maybe if we're going to look for life in our solar system and look for a place that maybe people could live someday, we should go to Titan, a moon of Saturn. Okay, so the very last thing I wanted to tell you is what's going to come next, right? As we try and find other planets in the universe that are like Earth, what are the next steps? Well, right now there's a spacecraft in orbit called Tess, the Transiting Exoplanet Survey Telescope. And what Tess is doing is trying to find as many planets that are near Earth as it can. So in the past, when we've looked for planets, we've mainly looked for planets orbiting stars that are very far away for a bunch of reasons. But Tess is focused on finding planets that are close. And the reason we want to find close planets is so that we can study them in a lot more detail. We can see them more clearly. And one of the telescopes we will use to do that is this one called the James Webb Space Telescope, which, if everything goes well, is going to launch later this year. And the James Webb Space Telescope is going to be the very first one that will enable us to study the atmospheres, the gases around these planets in a lot of detail and try and work out, is that little rock orbiting another star like Venus? Or is it like Mars? Or is it maybe like Earth? And that's what this very special space telescope, very, very complicated, probably the most complicated thing humans have ever built. It's going to launch hopefully later this year. And within a couple of years, we should start to be able to get a sense of which of the planets we've found orbiting other stars might actually be like Earth. And maybe, if we're very lucky, we'll find out if any of them have life on them. So that will be really, really exciting. Hopefully that's inspired you a little bit to think about some questions and we can get a discussion going. So I will thank you very much for your attention as we've learned a little bit about the search for another Earth and about life. Thank you so much. And if you have questions, I will very happily entertain them.
Okay, so now we are going to go into the asking questions period of this interview. And if you have a question, the link to post your questions is posted in the chat. So I'll be reading off the questions and Dr. Mike will be answering them. Okay, so the first question is, The Hedon Aeon, which lasted for about a gigayear, could be where microlife could have existed on Mars because it's a bombardment ended soon. Do you also think so, sir?
Yeah, okay, so this Hadean Eon, this was a period in the early history of Earth when uh, lots and lots of rocks from space were kind of smashing down on the Earth. And, you know, it was a terrible time, right? If you or I were there, we would die instantly. It's a terrible, terrible time in the history of Earth. However, it's also when life first began on Earth. Even in the worst period in the history of our planet, that's when life started on Earth. And we don't totally understand how that happened. How did life get going when things were so bad on Earth? I think the question was along the lines of, you know, could life have evolved under similar circumstances on Mars, right? Because Mars had a similar history, but its bombardment, you know, all the rocks hitting it ended soon. The honest answer is we don't know. We don't know why life started the way it did on Earth. We also don't know whether life even started on Earth. So if you think about it, you know, all these rocks hitting the Earth and making it a difficult place to live, one of the ideas people have had is, what if life hitchhiked to Earth on one of those rocks? What if life actually began somewhere else, maybe on Mars, and then hitchhiked to Earth on one of these rocks and started here? Or the reverse. What if life started on Earth and all these rocks hitting Earth broke some pieces off and they traveled to Mars and carried life to Mars? We don't know. So until we've actually been to Mars and kind of examined the surface more closely and tried to figure out, does it have life? Is it similar to Earth? I think we won't know the answer to this question.
Okay, so the next question is, the surface temperatures on Mercury range from well below 70 to 100 degrees, in spite of being in the too hot zone completely. Why?
Yeah, that's a great question. So we tend to say Mercury is a boiling hot planet, right? And yet that's true on average. You know, on average, it's a pretty hot place. And yet, as the question asker is pointing out, on some places on Mercury is really cold. You know, well below the freezing point. And you might wonder, why is that? It's right next to the sun. How could it be so cold? So the big difference there is that unlike Earth and Venus, Mercury has no atmosphere. There's no air on Mercury. And what air does is spread heat out, right? So if it's, you know, really hot on one part of the Earth, that heat will tend to spread out through the atmosphere and get distributed around. But on Mercury, there's no atmosphere. So one part of the planet can be boiling hot, but if another part is shaded from the sun, so if there's a, you know, a mountain or a cliff that's blocking sunlight, then the part that's in the shadow can be really cold because there's no air to spread the heat around from the hot place to the cold place. So that's why some parts of Mercury are extremely cold while others are extremely hot. There's no atmosphere to spread the heat out.
Okay, so the next question is basically asking, how many Earth-like planets have you found?
Yeah, this is a really hard question because it depends on how Earth-like you want them to be. But I would say we have found, you know, around kind of 20 or 30 planets that are pretty similar to Earth. But again, until we have something like the James Webb Space Telescope, we won't really know, are they actually like Earth, or are they kind of fooling us and they're really like Venus? But it's you know, a few dozen.
Okay, the next one is the other Earth Kepler 26b?
Yeah, so Kepler 26b. So again, when there was a space telescope called Kepler that found lots and lots of planets that are similar to Earth, and they all get numbered. So the star gets numbered and then the planets are lettered. So Kepler 26 is the star, and then B, C, D, E, F would be the planets orbiting that star. So Kepler 26b is you know, another one of these planets that I believe that one is also a sort of Earth mass planet, a sort of approximately Earth-sized planet. You know, as to whether it's another Earth, it's too hard to say right now. All we can say is that some of these planets are Earth-sized, but not necessarily exactly Earth-like.
Okay, the next one is, how does a planet lose its atmosphere? Can Mars have no atmosphere?
Yeah, so Mars doesn't have no atmosphere, but it doesn't have very much atmosphere. So how did that happen? Well, it happened in part because Mars is a lot smaller than Earth, right? It doesn't have it doesn't have a lot of gravity because it's small. And that means that the atmosphere of Mars can kind of bleed away into space. But it also happened because Mars doesn't have a magnetic field. So you may know that Earth has this big kind of force field, magnetic field that protects us from a lot of hazardous radiation from the sun. And that means that without a magnetic field like that, what happens is, particles from the sun, very high energy particles from the sun, bounce off of particles in Mars's atmosphere and push them away from Mars. And over millions and billions of years, that has allowed most of Mars's atmosphere to be stripped away so that it has barely any left.
Sir, there was life on Mars before humans existed?
Okay, so yeah, that sounds more like a statement. So maybe this is this person's belief, right? And maybe that's true. We don't know. The machines that we've sent so far to Mars, of course, we haven't sent humans yet, but the machines we have sent to Mars have never found really convincing evidence of life on Mars. But that doesn't mean that there was never life on Mars. We still need to kind of go there and explore more. So we're hopeful about future robotic missions to Mars, but maybe also human missions to Mars to see if they can find, bacteria in the soil or fossils or who knows what they might find.
So Ibrahim asks, a long time ago, Jupiter was small, and then it hit some asteroids, and then it got bigger. But when it got too big, it became gaseous, right, sir?
Yeah, that's basically it. So way back at the beginning of the solar system, there were no planets. There were just many small rocks orbiting the sun. And basically, as far as we can tell, the way you get a planet like Jupiter is you smash bits of rock together until you get a big lump of rock that's even bigger than Earth. And then eventually that lump of rock starts to gather gases, more and more gases, until you get a planet like Jupiter with a lumpy rock deep in the center, and then really thick layers of gas.
Okay, so the next one is, in the picture that you are showing, are all Kepler have a star? If yes, then how many?
Yeah, so what the Kepler Space Telescope did was stare at one patch of sky for many years. And it just tried to see for all the stars in that area of the sky, did any of them have planets? And there were, hundreds of thousands of stars in that patch of sky. And all the ones that we've been able to measure, there are many thousands of them. Almost all of the ones that we looked at in that patch of sky had planets. But, so there's thousands of them. But that number, you shouldn't interpret too much from that number, because we just looked at one patch of sky and only out to a certain distance. So as we get better and better telescopes and more of them, looking all over the galaxy, we keep finding planets around almost every single star. So basically every star in the Milky Way has planets of some kind. So it's hundreds of billions of planets in our own galaxy.
So what is the first Earth-like planet that we found?
Yeah, so what the first Earth-like planet, again, it depends a little bit on how Earth-like. If you go back and look on the internet and try and look up first Earth-like planet, you will see, in the 1990s, people were claiming planets that were not even a little bit Earth-like were Earth-like, because they were just being optimistic. So I would say, there's so far we have never found any planet that we are 100% sure is like Earth, but there are some that are pretty good candidates. Exactly which one, it depends a lot on your criteria. So I wouldn't name one in particular, but there are a few dozen that are good candidates.
Okay. Is there a new technology which makes space travel faster?
Yeah, there's always new technologies to make space travel better and faster. So, a lot of the space travel that we do these days is using chemical rockets. So we use, basically the same kind of reactions that happens in, car engines and whatnot. You use a kind of chemical reaction to create basically an explosion that pushes a rocket off the Earth and then through space. But nowadays, there's a couple of other new things that people are trying. One is something called a solar sail. So that's where you basically use a giant mirror in space and it literally sails on sunlight the same way that a sailboat on Earth sails on the wind. That isn't necessarily faster in the sense of moving very, very quickly, at least initially, but it can build up to being very, very fast after it has received enough sunlight. And then there's another one called an ion engine, which is a slightly different way of moving around the solar system. And if we can get a really good ion engine going, we could probably get to Mars, for example, a lot faster than we can currently.
What are your thoughts on the James Webb Telescope? What makes it different from the Hubble telescope?
So when astronomers make new telescopes, often one of the things that we're trying to do is just make them bigger, because a real limiting factor in astronomy is how big a telescope is. The bigger the mirror on a telescope, which is the thing that gathers the light, the more detail we can see for distant objects. So the Hubble Space Telescope has a mirror that is about 2.5 meters in diameter, right? It's about as big as, me holding my arms open. But the James Webb Space Telescope has a mirror that is, I believe, more like 8 meters in diameter, something like that. And so that's, several times larger than the Hubble Space Telescope. So one of the things that will allow us to do is see further away in more detail. But it's also a different kind of telescope. It uses a different kind of light than the Hubble Space Telescope does, which will again be make it a little easier to study things like the atmospheres of distant planets. So it will be a huge step up over the Hubble Space Telescope.
Okay, the next one is, sir, what is a wavelength and what are microns?
What is a wavelength? A wavelength is, if you think of a water wave, right? If you go to the ocean or even just in a bathtub and you kind of bounce the water and make a wave, right? A wavelength is the distance. So if you think of a wave having kind of peaks and valleys like that, a wavelength is the distance between two peaks. So what does that actually mean? For light, the wavelength of light is what determines the color. So red light has a long wavelength, blue light has a short wavelength. What's a micron? A micron is a millionth of a meter, and it's just a measure of wavelengths, basically, or anything that's very small.
Okay. Do you believe in the antimatter universe? When do you think humans would be developed enough to make spacesuits out of energy and not get exploded?
So an antimatter universe. Well, so here's the thing about antimatter. A lot of people hear about antimatter and they think, oh, it's some kind of science fiction or some kind of thing that isn't real. But actually, there's antimatter all around us. The sun is making antimatter all the time. Some experiments on Earth make antimatter. Antimatter is unusual, but it's not fictional. It's a real thing. And as far as we know, there's no universe made of antimatter, but I can't say that there isn't a universe made of antimatter either. So when do I think humans will be able to make spacesuits out of energy? That sounds really hard. I think I would not know how to do that, but maybe you will know how to do that. Some of you will be, when you grow up, you might become scientists and figure out how to do something like that. That would be wonderful.
The next one is, what is your favorite planet?
What is my favorite planet? Oh, it's hard to choose a favorite. I think if I had to choose one planet that, I would really want to go to, it would probably be Mars. Mars is, as I say, the one that is in our solar system, the one that humans would have the easiest time probably surviving on. So that's probably where I would go if I could.
The next one is, do you think scientists have plans to keep telescopes on these planets, which could capture a lot of other space objects?
So we would love to do that. That's so far in the future. Even with the very best rockets we can imagine today, we still couldn't even send humans out of our own solar system. We even to the very nearest star, we couldn't send humans there, not for a long time, because we just don't know how to build a rocket that can go fast enough, safely enough. However, what we're more likely to do in the near future is build telescopes on the moon, because if you can put telescopes on the moon, it's relatively cheap to build them compared to building space telescopes that you sort of push into space and then hopefully they work, because you can't really go and fix them because they're floating by themselves in space. It's a bit cheaper to build them on a solid surface that humans can visit. But the advantage of the moon is that there's no atmosphere. So you don't have to deal with all the air and the light pollution and things on Earth. So we will probably build telescopes on the moon before too long.
Okay. Is Kepler 452b in the Milky Way?
Yeah, so all the Kepler planets are in the Milky Way. They're all relatively close to us just because of the way the Kepler Space Telescope works. It doesn't see planets that are, beyond our galaxy.
Okay. Could you speak about some major contributions of the Canadian Space Agency?
Yeah, so the Canadian Space Agency is, maybe some people don't even know that Canada has a space agency because it's not, as flashy as the NASAs of the world. But one of the things that the Canadian Space Agency has been really good at historically is robotics. So Canada doesn't build a lot of rockets and launch them into space, but it does build robots. So for example, the International Space Station has always had arms on it that were built by the Canadian Space Agency to help the astronauts, build the space station and manipulate pieces of it. The Canadian Space Agency is also really good at building satellites. So Canada builds satellites for countries all over the world, in particular, often small satellites, very efficient little tiny satellites, and launches them. And then of course, we also launch people. So we have a number of astronauts from Canada who have gone on the space shuttle or to the space station. So those are some of the things that Canada is good at.
When and how did the Earth become the Earth we know today? Did it really collide with Mars?
Okay, Earth never collided with Mars, but it did collide with an object that would have been similar to Mars. So a very long time ago, back, like I mentioned before, when the solar system had lots of kind of rocks floating around the sun, but not a lot of planets, or planets were still forming, when Earth was just kind of baby Earth and it was just getting going, it did collide with something about the size of Mars, and that broke off some stuff, and the stuff kind of went out into space and eventually turned into the moon. But then in terms of when did Earth become, like it is now, again, that really depends on exactly what you mean by like it is now, but I would say it was pretty recently, maybe about 500 million years ago. Before then, so that's most of Earth history. 500 million years sounds like a long time, but that's really recent in terms of Earth's history. Before that, life on Earth was mostly not at all like it is now. It was ocean life mostly. A lot of it was not oxygen breathing and things like that. It was quite different. So Earth that you would recognize is kind of basically similar to the Earth of now is not all that long ago.
Emeka asks, we are dreaming of colonizing exoplanets while we are unable to fully shield our own Earth from global warming. Can we expect a successful civilization there?
Yeah, that's a really hard question, right? This comes up a lot as to, where should our priorities be? Should we focus on, fixing the problems we have on Earth, of which global warming is a really big one? Or should we, try and go to some other planet? And people are very divided on this question. Some people are very convinced that we should leave space exploration until we fixed our problems on Earth. And other people think, our problems on Earth are so bad, we should leave. And I'm on neither of those sides. I would say we should do both of these things. We should definitely put all of our effort that we can into fixing the problems we have on Earth. We have pretty bad problems with pollution and global warming and things like that. We should fix them. And those are fixable problems. They're not even going to be that hard to fix. We just have to find the willpower to do it. They'll be challenging, but not impossible. But once we get off the Earth, I think there are separate, really good reasons to want to leave Earth. We want to be able to answer questions like, is there life elsewhere in the universe? We want to explore because that's part of what makes us human, is this desire to go out and explore new places. So I think we should take care of Earth, but we should also leave, or some of us should leave and go and explore elsewhere.
The next one is, according to NASA, the Voyagers were about to lose communication with Earth. However, this, as they say, has been delayed. When will they lose contact with us?
Yeah, I honestly don't know the answer to this. So the Voyager spacecraft were launched in the 70s and 80s, I believe, and they're old now. And we kind of keep expecting that we're going to lose contact with them at any point, and then engineers keep doing miraculous things and keeping contact going. So I genuinely don't know when they're finally going to lose contact permanently with Earth, and whether that will be because they actually lose the ability to communicate with Earth, or just that we give up on talking to them. I don't know which of those is going to happen first.
The next one is, sir, Mars had water billions of years ago.
It did, absolutely. Yeah, Mars had oceans, not very thick oceans, but it had oceans billions of years ago. Yep.
Can Mars be a habitable zone?
So maybe you mean, can Mars be in the habitable zone? So again,
Yeah.
it sort of depends. A long time ago, when Mars had water, we would have said, yeah, it's in the habitable zone. But today, because Mars's atmosphere has changed and mostly gone away, we would probably say Mars is not in the habitable zone, or it's just on the edge of it.
The next one is, but you can't just throw a planet. That should not be a person's mindset. We must save Earth, and when the population crosses 10 billion, a few of us will leave. I think that's a statement.
Yeah, sure. I agree completely. We definitely need to do all the things that are, our responsibilities to take care of our own planet. Absolutely.
It says, have you worked with the Indian Space Agency?
I have not personally, but some of my colleagues have. Yeah, I have not myself, though.
What is the measure of ATM at Titan?
Okay, so ATM is a measure of atmospheric pressure, right? It's a measure of how thick and dense the atmosphere of a planet is. And on Titan, the atmosphere is a bit thicker than on Earth. I actually can't remember the exact number, but it's similar in thickness, but I believe a little bit thicker than the atmosphere on Earth.
Okay, the next one is, if James has 3 apples and Sarah has 2 pears, what is the percentage of gravity on Mars?
I'm honestly not even sure what that means.
I think they're asking, like, what is, like, the G-force? Oh, wait, not on Mars. Like, what is the G-force on Saturn?
Well, so that again, that's a really, we can say, like, what is the gravity on Earth? But when we ask that, what we're basically saying is, at the surface of Earth, what is the gravity? But Saturn doesn't really have none of the gas giant planets have like a solid surface that you could stand on and say, at this place, what is the amount of gravity? So instead, the amount of gravity varies depending on how close you are to the center of the planet, from much less than Earth to much more than Earth.
Is the presence of phosphine on Venus is the sign of life there?
Yeah, so you may have heard recently there was this big story in the news of this chemical called phosphine that was discovered in the atmosphere of the planet Venus. And this was exciting because phosphine is what we sometimes call a biosignature, meaning a thing that points to the presence of life. So similar to oxygen in the Earth's atmosphere, there is oxygen in Earth's atmosphere because there are plants on Earth. The plants put the oxygen in the atmosphere and keep it there. Phosphine is sort of similar. People imagine that, phosphine probably wouldn't exist in a planet's atmosphere if there weren't life there, because other processes would get rid of it. So when there was this announcement of phosphine detected on Venus, the suggestion was this meant that there might be some kind of life on Venus, maybe living in the clouds where it's not so hot. However, other astronomers have gone back and checked that. And actually, it looks like right now, it was a mistake. There is apparently no phosphine in the atmosphere of Venus. So if it had been there, it might have been a sign of life, but it looks like that was actually a mistake and it wasn't there.
Next one is, how did Mars lose its water?
How did Mars lose its water? Basically, it lost its water along with its atmosphere. So water is made of hydrogen and oxygen, H2O, we say. And as Mars was, so some of the water evaporates into the air, and then the hydrogen and the oxygen can get broken apart, and then they can individually escape into space, which is basically what happened.
Okay, the next one is, can gravity form waves?
Yeah, gravity can form waves, and this is super, super exciting. This is a big new area of research in astronomy. So this is a little complicated, but the basic idea is that anything in the universe, literally anything, from stars to planets to people to specks of dust, anything that has mass makes gravity. And gravity can be thought of as a kind of dent in space. So you can think of the sun as making a big dent in space, like a funnel, if you like. And Earth is stuck in that funnel, going around and around in the funnel. But if you move the sun, then the funnel that it makes also moves. And in just about everything in the universe is moving in some way. And because everything in the universe is making tiny amounts of gravity and also moving, it's making these kind of ripples in gravity that spread out through the universe. So until recently, we weren't able to prove this and detect it. But now there are these 2 or 3 really big machines called gravitational wave interferometers. And they have been able to detect the ripples in space, these gravitational waves caused by black holes, enormous, enormous, massive objects that are very, very, very far away.
The next one is, what lies after the Kuiper belt?
So the Kuiper belt is this place in the outer solar system after basically the planet Neptune. And it's where a lot of comets live. So you may know that between Mars and Jupiter, there's something called the asteroid belt. And then after Neptune, there's something called the Kuiper belt. And the Kuiper belt is filled with a lot of very cold, icy objects that often wander into the inner solar system and become comets. And then beyond that, there's an even bigger cloud of comets called the Oort cloud, which goes way, 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 way further out from the sun, almost to the nearest solar system. And sort of beyond that, there's just the emptiness of space until you run into other solar systems.
The next one is, what is the significant importance of exploring the moon's south pole and comparing to the other pole?
The moon is not something I know as much about, so I'm not sure specifically. I think part of the interest lately in exploring the moon's south pole is that there are craters, just as I mentioned with Mars. If you get these shaded areas where sunlight doesn't ever reach, then you can have very different conditions in those areas. So, for example, on Mercury, if you had a crater that was permanently shadowed from the sun, no sunlight ever reached it, you could actually have ice sit in that crater, even though the rest of Mercury is boiling hot. It's kind of similar on the moon. I think there are craters at the south pole of the moon people are interested in looking into because they think there may be deposits of ice that have been hiding in those craters. And I guess also we just haven't really been to the poles of the moon to explore them and see what's going on.
The next one is, does every black hole contain a singularity?
We'll go with yes. As far as we know, yes. Singularity is basically what happens when anything that's very, very massive, often a star, collapses and forms basically an infinitely dense point. And although we're not completely sure what's going on inside black holes, the currently prevailing idea is that every black hole has a singularity. But of course, people are kind of, we say that fully understanding that we don't really know what's going on in there. So singularity is the best idea currently, but we're willing to consider other options.
So the next one is, are there astro programs in Canada to engage children and make this as a hobby and develop their skills?
Yeah, there are. So one of the best ones, maybe not during a pandemic, but once we're back out of this, the best place to go, depending on where you live, nationally, you can go to the Royal Astronomical Society of Canada, RASC. So their website is rasc.ca. And they run all sorts of different programs for people of all ages. So if you want to, for example, learn how to use a telescope, they run clinics and they run kind of meetings in their communities to talk about astronomy and how to learn more about it. And then if you happen to be in Quebec, there's a similar organization called the Federation of Amateur Astronomers of Quebec. Those are two great organizations.
Okay, the next one is, does the influence of gravity extend out forever?
Yep, that's another easy yes. Yes, it does. Yep.
Can the moon have water? And if yes, can we live on the moon?
So this is interesting, the difference between a moon and the moon. So moons in general can have water. As I showed you, moons of Jupiter like Europa have loads of water. Whether we could live there is a bit iffy because it's locked under thick layers of ice that we probably wouldn't want to live under. But in terms of the moon, meaning our moon, the moon of Earth, could we live there? Absolutely. There's not a lot of water there, but there's a little bit in some of the soil. And we would probably also wind up bringing water from Earth and things like that. So we could live there. We wouldn't want to unless we were there for science. You know, it's not a place you would go for a vacation. It's not very hospitable, but you could live there.
So Lilu asks, why does Venus have a thicker atmosphere compared to Earth?
Yeah, that's a tricky one as well. So the way we think of this is that so there's it gets a bit complicated. On Earth, we have something called the carbon cycle, which is this sort of, I'll just give you a quick sketch of it. So on Earth, let's say you have a volcano. Volcanoes erupt gases into the atmosphere. Some of those gases wind up dissolved into the water in the atmosphere. Then it rains. That comes back out and gets you know, the gases wind up getting deposited in the ocean. Organisms in the ocean consume that material, they die, their bodies float to the bottom of the ocean. They eventually become sedimentary rocks, which go back into the earth, get molten, and then come back out of a volcano eventually. So you get this complete cycle where material from the atmosphere is always being returned into the earth. But on Venus, that cycle shut off a long time ago. And so as volcanoes continued to erupt, they just belched all their gases into the atmosphere and nothing ever really left. So that's part of why Venus has a thicker, particularly carbon dioxide atmosphere than Earth.
So the next one is, what is the sun's fuel or heat?
The sun's fuel is hydrogen, the very simplest element in the whole universe. And what stars do, particularly stars like the sun, is they take atoms of hydrogen, they smash them together, and they turn them into, in the case of the sun, they turn them into helium. So you turn hydrogen into helium, and that releases a little bit of energy, and that's what powers the sun.
The next one is, sir, is there any type of telescope to see the sun?
Absolutely. There are so many telescopes that are devoted to studying the sun. So if you mean kind of professional telescopes, yeah, there's tons of them. So one that's really exciting right now, you could look on the internet, is called the Solar Dynamics Observatory, SDO. And it's a spacecraft that's staring at the sun all the time, producing gorgeous pictures and movies. But if you're thinking about, you know, you want to do this on Earth, maybe, yes, you can usually fit a telescope, any kind of telescope, with a special film that blocks almost all sunlight and just lets a tiny bit through so that it's safe. Just be careful though. If you're going to try something like that, you can permanently ruin your eyesight. You have to be completely sure you have exactly the right special type of film. There's a lot of misinformation out there about things you can try. For example, some people imagine, you know, use candle smoke on a piece of glass. Do not do that. You can permanently burn your eyes before you're even aware. So just be careful.
Okay, so the next one is, radio waves travel at the speed of light. Would there be a change during their travel to distant planets since time would never pass for them?
That's quite complicated. We would have to go into that in a little bit more depth, but yes, time does pass for radio waves as they travel at the speed of light in one sense, but there is also, yeah, there's something called time dilation, which affects, it's a complicated issue. It would take a while to go into, but there is something called time dilation that you have to account for if you know, radio waves travel long distances through the universe and things like that.
Okay, the next one is, have you found a planet yourself?
I have not actually found a planet myself. That is not my particular area of research. So no, I unfortunately haven't, but I work with a lot of people who have, so.
Next one, what is the nearest galaxy to us after the Andromeda Galaxy?
So this is another one of those depends on your standards kind of thing. So the Andromeda Galaxy is a big galaxy like the Milky Way, very similar in size to our own galaxy. And beyond Andromeda, there is another fairly big galaxy called Triangulum, which is, again, roughly comparable in size to the Milky Way. But there are actually even closer, some very small galaxies. whose names I don't even know because they're so small we usually don't think about them. But there are actually some small ones that are even closer.
Next one says, a silly question. Did you like the movie Interstellar? Is there anything true in that movie?
I did like that movie, and there's plenty in that movie that's true. So for those of you who've seen it, I just mentioned in response to another question this concept of time dilation. And Interstellar does a wonderful job of portraying this concept of time dilation. So in that movie, there is a big black hole, and there's a planet, I believe multiple planets, if I remember correctly, orbiting this black hole. And you may remember there's a part where some of the crew are orbiting far from the black hole, and other ones go down to the planet that is closer to the black hole. And when they come back to their colleagues on the ship, their ages are no longer what they once were. They've come out of sync with one another in time. And that is a very real phenomenon. If you were on a ship orbiting a black hole with your friend, and then you went close to the black hole and came back, by the time you came back, your friend, maybe the trip took 2 days for you, your friend might have aged 20 years. That is a very real phenomenon that actually happens. It's never happened to a human before because we've never been anywhere near a black hole. But that part of that movie is true.
The next one is, do you think asteroids still collide with the Earth? Could you name a recent event?
Yes, asteroids definitely still collide with the Earth. Again, there's an issue of scale. So tons of asteroids collide with the Earth every day, but they're microscopic. So we usually don't think of them as asteroids. We think of them as meteoroids. But occasionally larger objects have collided with the Earth. So there was an issue, or there was an event in Russia several years ago, around kind of 5 or so years ago, when a decent sized object, it didn't actually hit the ground. What tends to happen is they explode in the atmosphere when they heat up. And so it exploded in the atmosphere and shattered all the windows in this city in Russia and, set off all the car alarms and things like that. So it does happen.
The next one is, sir, do you know what is the oldest thing in the universe?
The oldest thing in the universe is the universe itself, basically. The very oldest thing is all of the gas and light that started when the universe, as far as we know, started. But in terms of kind of more familiar objects, stars and galaxies and things like that, the very first objects to ever form in the universe, the very first stars, have all died a long time ago. They lived for a very brief period of time and then died. And so after that, there's another generation of stars that are almost as old as the universe, but not quite. And there are many of those around, lots and lots of them.
The next one is, Huygens spacecraft, as you might know, took pictures of Titan's surface and found traces of rainfall that rained there. Water?
Yeah, no, it's not water that rains on Titan. It's, these gases, ethane and methane, that those oceans are made of, and probably plus some other chemicals we haven't quite worked out yet, that evaporate into the atmosphere, and they form clouds, and eventually they rain back down into the oceans and rivers of Titan.
The next one is, who cleans the space debris created by us?
A very sad answer to this question is basically nobody. So when we leave junk in space, a lot like the way we treat the surface of the Earth, when we leave junk on Earth, we just leave it there, which is sad and the wrong thing to do. Maybe we push it into a hole someplace, but we just leave it there. And we do, unfortunately, the same thing in space. When we send spacecraft up into space, sometimes when people are done with their spacecraft, they push them back to the Earth and they burn up in the atmosphere. But other times they just leave them there. And now there's a whole lot of junk orbiting the Earth, which is going to be a problem very soon. It'll make it difficult to go into orbit safely.
Next one is, sir, what is the difference between a black hole and a white hole?
One difference is that we're sure black holes exist, and we don't know if white holes exist. So a black hole is what happens when something like a star collapses and becomes so dense that it sort of seals itself off from the rest of the universe with this one-way barrier we call an event horizon, that you can only go in but never come out. A white hole is a theoretical object, an object we're not sure if they exist. We've never seen one. But the idea is that it would be sort of the back door to a black hole. So things that fall into a black hole could come out a white hole. But we don't know if there is such a thing.
Next one is, can placing a magnetic dipole between Mars and the sun help the planet in building an atmosphere by protecting it from solar winds and building a magnetosphere?
That is not an idea I have come across before. I don't think so. So giving Mars some kind of shield from the sun to prevent the sun from stripping away the atmosphere of Mars would um, help protect Mars, but it wouldn't generate an atmosphere because there just isn't anything on Mars that would produce an atmosphere. The kinds of ways people talk about producing an atmosphere on Mars would be, for example, to melt the ice caps of Mars so that they become gases. And then, yeah, you would probably want something to prevent the sun from just stripping all of that away again.
Okay, the next one is, why haven't we found life yet in the Goldilocks zone? Is there liquid water there and an acceptably good atmosphere? Pressure equals 1050 HPA.
So the Goldilocks zone is another word for that habitable zone that I mentioned. It's the range of distances around a star where it's neither too hot nor too cold for a planet with liquid water to remain. So of course there is life in the Goldilocks zone of our solar system, and we are that life. Earth is in the Goldilocks zone and we are alive, as are other things on our planet. But in other solar systems, it's not so much that we can say there isn't life. It's just that we don't have the ability yet to detect life. So we know, as I mentioned, about lots of planets that are basically Earth-like and they're in the Goldilocks zone of their stars, but we just don't have the ability to be sure that they either do or do not have life yet. We need bigger telescopes for that.
Yeah,
Okay.
Rafael, we are almost at the end. Maybe we can take one more question and after that we can conclude.
Okay, so the very top one we've already done. This one says, sir, my doubt is that K2-18b planet, the twin Earth found by Stephen Hawking, is also the planet that we can live in. So, sir, can you explain about K2-18b?
Okay, so that's a really good question. And I'm going to, there's a lot of Kepler planets. I'm going to look that one up really quickly to remind myself of which one 18b is. Okay, so Kepler 18 is a star that is very similar to the sun, and it has 3 planets, all of which are what we call super Earth. So the smallest of them is about 7 times the mass of the Earth. So that would, in my mind, probably not be an Earth-like planet. We're not completely sure. That's a kind of planet we don't exactly have in our own solar system. It's sort of somewhere between an Earth and, say, a Neptune. And it's in this sort of awkward middle region where we're not actually sure, is that kind of planet going to be a big rock like Earth? Or is it going to be a smaller rock but surrounded by a whole lot of gas like Neptune? If it's a very big rock like Earth that maybe has some kind of nice atmosphere and maybe liquid water, yeah, it could be Earth-like. It would be different from Earth, much stronger gravity, probably a much thicker ocean, probably a thicker atmosphere, but it could also be like Neptune and be completely unlike Earth. So that's where we really struggle, because one of the things we've learned in looking for other planets like Earth is that the set of planets in our own solar system are just a small fraction of the possible types of planets. There are many kinds of planets that exist. We have nothing like them in our own solar system. And this would be one of those kinds of planets. So we just don't know enough about them yet to say whether they would be habitable.
So I do believe that is the end of our question session. Thank you, Dr. Mike, for speaking with us today. And I will pass it on to Dilip Uncle.
Okay, thank you, Professor Mike, and thank you everyone for joining.
You're very welcome, everybody. Thank you so much for tuning in. I really appreciate all your questions and your attention. It was wonderful to speak to you.
Thank you.